Hello and welcome once again for another video. This will be the lecture video day 2 part B. It'll be the final video for day 2. The final lecture video. There'll be another example problem video coming shortly. The where we left off last time was this concept of quasi-equilibrium or quasi-static processes, which I had not started yet. So let's describe what that is. A quasi-equilibrium process is a process that reaches equilibrium at each point in time from beginning to end. Or put another way, it goes through a series of equilibrium points. So typically when we think of a quasi-static process, we think of something that's going slowly, although really it doesn't have to be too slow. It just has to be slow enough that it can be approximated by each point in time having an equilibrium. Okay, this is definitely not true of any process. It's an idealization, but it works quite well in many scenarios, as we'll see in the problems that we do. And what it means basically, for our perspective, is that at each point there is a well-defined, say, pressure, a well-defined volume at each point across the entire process. There is a well-defined pressure, temperature, volume, any of those properties that we've already discussed at this point. So let's go right into our second clicker question. And again, make sure you take down the answer so you're prepared in class when you come. Which of the following processes could be understood to be quasi-static? So I'm going to give you this figure. We have the one that is shown in red, where the pressure and volume are only known at each of the end states. We have the one shown in black, where the pressure and volume are known at each point along the way. So which of those would be quasi-static? The scenario in red, the scenario in black, neither of them, or both of them? Okay, so let's move on. Is work a property? This is a very good question, right? Up to this point, all of the stuff that we have discussed has been properties: temperature, kinetic energy, potential energy, volume, pressure. I don't know if I said that twice, but there you go. So all of these things that we've discussed thus far, they're all properties. So is work a property? Well, let's take a look at a picture down here, and we'll get the idea of it's going to tie in very nicely with inexact and exact differentials, because these are going to be closely related to each other, whether or not work ends up being a property. So what is an exact versus an inexact differential? Well, an exact differential would be something like this: dV, where V is the volume. I can think about a little element of volume, and I can do things with this, including, say, take the integral from V1 to V2 as an example of dV. And just you should remember that this is a pretty simple integral, that this should end up being V2 minus V1, right? Integral of dV is just V, and then we substitute in the endpoints there, V2 and V1, and we get V2 minus V1. Okay, now notice that this integral, the only thing that matters are the endpoints, right? So for a property, it doesn't matter what process happens, the property always has well-defined values. Okay, so for a property, such as volume, It always has well-defined values regardless of what's happening. Whatever the process is, it always has these nice well-defined values, uh, at least in a quasi-static process. So it always has these well-defined values, and it doesn't matter. Sorry, it doesn't matter the process, right? So it always has these well-defined values. Now, in the case of work, notice that we have this process A that I'm going to show right up here, process A, which the amount of work done, by the way, we can always think, we're gonna come back to this over and over again, but we can always take a pressure versus volume diagram and we can get the amount of work done. Did I write it up here? I don't know. I didn't write work in that way yet, but I probably should write work in that way. So work, by the way, is equal to the integral of the pressure as a function of the volume times an element of the volume from V1 to V2. So this is another way, this is capital W, and this is the work. This is another way we can define the work done. Okay, so the work done in this case is equal to this integral. And the nice thing about that is that if I plot this on the pressure versus volume axis, then the area underneath whatever curve that happens here will give me the work, because that's really what an integral is, right? We're thinking conceptually about it in terms of being a volume under some kind of curve, right? So notice that I have some functional relationship here of the pressure to the volume. It seems like a nice smooth curve, so it's probably a continuous function for at least going from process 1 to 2, or going from state 1 to 2, excuse me, in process A. And the orange shaded region here, this region that's shaded in orange here, that goes all the way down to the bottom. Notice I have orange all over the place here. That whole thing is the amount of work done in this process. Now for process B, notice I have a different functional relationship going from state 1 to state 2. And the purple region that's colored in, I'll just circle all the purple here. This whole thing underneath this curve, that area would be the work done in that case. Now notice that the amount of work done depends on the process. Now we talked about up here, the volume, which is a property, doesn't care about what process is happening. It always has these states, V1 and V2, whereas the work, it does matter what process is happening. So I have process A and process B, and they're going to give me different answers for the work. So work is process dependent. Therefore, it needs a inexact differential. So we would actually think about this as being the integral of the inexact differential dw, delta w, that's a lowercase delta. So when we use delta, that means it's an inexact differential, and you can immediately, so it'd be the integral of that thing, you can immediately tell that anything that has this delta notation is not a property. So this is not going to be a property. We need an inexact differential, and the reason is we have some path. Let's call it from S1 to S2. The path matters. Notice that the path from 1 to 2 here is different than the path from 1 to 2 here. So it's path dependent, and that's why it's an inexact differential. Okay? So an exact differential, it doesn't care, we don't care about the path, only the endpoints. So we can think of that in terms of a normal integral. Whereas the inexact differential, notice here that we have some function that we're dealing with, that we're taking the integral of, right? So an inexact differential means that we have to define whatever that function is first before we can figure out what the value of the integral is. So we have to, in this case, the pressure is a function of the volume, some kind, in this case, in the two cases that I showed here, some nice smooth function of the volume, but it is a function, and we have to define that function first in order to figure out what the work is. Whereas here, we don't have to define any function. We just take the integral and we can find it, right? So that's the difference between the exact differentials and inexact differentials. And so work is not a property. It's path dependent. So we're going to see this in all of these different ways. Path dependence means that it's not a property. The fact that it needs an inexact differential means that it is not a property. The fact that it needs a function defined before we can determine the integral means that it is not a property. Okay? Okay, so the last topic that I wanted to cover for today was, so we were talking about quasi-static processes, and then we jumped to the work. Is the work a property? But let's go back to the quasi-static processes for a moment. There's a special type of quasi-static process called a polytropic process. And why we care about this is that it has a nice functional form. So this P of V here will have a nice functional form that we can deal with. It doesn't have to take this functional form. The only ones that take this particular functional form are called polytropic processes. So a polytropic process is one. Let's actually just write this all out. Is one in which P times V to the N is equal to a constant. Now, if I use, let's make C a constant here. That means that I can actually find the functional form of P in terms of V very easily. In fact, P is equal to C divided by V to the N. Oh, so we would say P of V is equal to C over V to the N, right? So now we actually have a functional form. In this case, the polytropic process always has a functional form, and we can actually determine this constant if we're given the right amount of information. We'll see that in an example problem. But if we're given the right information, we can determine the constant, and then we can substitute it back into this integral. Right now we'll have P as a function of V. This is going to be the functional form of it when it's a polytropic process, and we can use that to determine the value of this integral. Okay? That's all that I have for this video. Hope to see you again soon.